Let's go ahead and get started. So today we are starting a new unit. It is another short unit. It's not very long. Okay, it's just on nuclear. So we're starting today, which is Monday. Next Tuesday we have the test. So it's really quick and fast, and it's a pretty easy unit. But it's just a taste of what nuclear is. We're not going to go very deep into it. We're just going to touch the surface. So let's go ahead and get started with nuclear chemistry. Just a reminder, those that are due on the 17th, I've put your names up on the board so you know that you're due. Don't forget, if you're the 21st or 23rd, that you need to make sure that you're not procrastinating your project. Make sure you're working on it. After our test on the 7th, you'll have 3 days in class. If you're a sophomore, you'll only have 2 days in class to work on the project, and then we'll start presenting. The 7th is our test, and then we'll have 3 days after that, and then we'll start presenting on the 17th. Okay? All right, so I like this little cartoon, Calvin and Hobbes. I don't know how many of you like Calvin and Hobbes. Here's a little town. Here's a steam shovel scooping out a giant hole. Here comes a bulldozer pushing thousands of barrels of toxic nuclear waste into the giant hole. Over the years, these dangerous poisons seep into the underground waterways. The cancer rates in the nearby little town triples. If you want me, I'll be under the bed. Okay, so a lot of people, when you say nuclear, they just freak out. They just get really scared. So we wanted to go into what is actually going on, maybe. It doesn't want to move forward. Let me try and hardwire it over here. Okay, so we are going to be working with nuclear vocabulary today. Symbols, equations, half-lives, and intensity. We're going to do a nuclear decay activity at the end. You like the Superman thing, hold on, you can't be in here, the suit's power core, it's radioactive. But there's Superman, you know. Okay, so the first thing we're going to talk about really quickly is, I don't know how many of you have been personally touched by radiation, in other words, cancer therapy. But this lady, Tamara, she was my sister-in-law. And she was 33 when she died of leukemia. She first had thyroid cancer and then leukemia. And thyroid cancer is actually on the rise. And it is a butterfly, the thyroid is a butterfly thing right in your neck. And if you start feeling lumps on it or bumps, those could be cancers. What they do is these cancers are rapid growing. And it's actually the 5th most common cancer for women. They take what's called seed crystals and they place them in the cancer. And then they do radiation, and those seed crystals basically burn the cancer from the inside out. But what usually has happened in the past, I mean, this was 2003 when she lost her fight with it. But what has happened, they're finding out, is if they treat thyroid cancer like they have in the past, it actually causes leukemia. And the people end up dying from leukemia a couple years after they finish treatment. So that's just something that's impacted my family. Radioactive nuclei. So we need to know basic radioactive nuclei. And you've got this picture, and you've got beta, alpha, and gamma rays. Gamma rays are extremely high energy. This is the red ray. The blue rays are beta rays. These are basically what electrons are. And the alpha rays are a helium nucleus. In other words, the electrons have been bounced off of them. To give you an idea, alpha rays can be stopped by paper. So if I have paper, it will stop an alpha ray. A beta ray will get somewhat through your skin. Okay? It shows it's stopping here, but actually there's some that comes past it, and wood will stop it. A medical X-ray, you need to have 5 feet of concrete or 10 centimeters of lead to stop it. Gamma rays, 5 feet of concrete will slow it down. There'll still be some coming through. Neutron will go right through 5 feet of concrete. So we worry about more than neutrons, because neutrons can actually affect our DNA. So again, thick lead reduces gamma but does not stop it. So let's do some definitions. The first one here is radioactive nuclei. This is nuclei that undergoes spontaneous change and emits energy in the form of radiation. Radioactive decay is a process in which an unstable nucleus changes energy states, and the process emits radiation. And the third one is radioisotope. an isotope of an element that emits nuclear radiation. So you'll notice all of these have a common factor. They emit radiation. Now when we've done equations in the past, we've worried about the electrons on the outer shell. But remember our snowflakes here? We're now going to start with nuclear equations. That's what nuclear chemistry is all about, is the nucleus, the protons and the neutrons. And what happens when I have an unstable proton-neutron mix and how it comes apart. Okay? So this is what we're going to be worried about. Radioactivity, which is where we emit decay. Are we all right?
Question.
Yes.
It said that what's called cell phones and microwaves give off
Radiation.
radiation. So is that harmful for you?
It depends on how long you've been around it. They were finding that if you have the cell phone up to your ear too long, that it was causing tumors behind the ears of the old kind of cell phones. Now they've made it so they don't have that much, but as much as you guys are using it, they're still finding more cancers that are related to the electronic equipment that you guys are using now. Oh, we're all going to die. Right? Just depends on how. Okay, we okay to go forward? Okay. Yeah. So alpha particles. These are things that these are the three big ones that we're going to be talking about. We'll add a few more to this. But alpha is identical to a helium atom, except it's lost its electron, so it has a positive charge. Beta is identical to an electron, but it is produced when a neutron from the nucleus splits into a proton and an electron. And a gamma ray is a very high energy ray that is like an X-ray, but it has a lot more energy that's given off. We good to go? Need a few minutes. High energy ray that is like an X-ray but with higher energy. Got it? Okay, going forward. This is what I would like you to add up at the top where you have that picture that has alpha, beta, gamma. These are the particles we're going to be using, and you need to know how to write them. So when it says or, you can choose how you write it, but you need to be able to identify it both ways. Now, oftentimes they won't put the 4-2 by the alpha, the little thing that looks like a fish. They'll just put the fish, and you have to know that it's an alpha, and put the 4-2 there. Same thing with the beta. Sometimes they'll just put a beta, and they won't put the 0, -1 with it. A positron, they have to show you that it's a +1. That it's not the negative. A neutron, again, they could just put a lowercase n and assume that you know it.
Oh, this is what?
The headphones cause the same radiation.
Depends.
Just wired ones.
Wired ones shouldn't. Okay, has everybody got these down?
All of that.
All of it. We're going to be using these a lot, so you'll want to make sure that you have these down. And you guys are lucky because I had it more complicated on the other one.
0, then under -1.
Yeah, it's a fancy, weird-looking B, yeah. It's a beta, it's a Greek symbol. You can put them back on wherever you want them to.
Is that an E? For beta?
I'm probably going to have you redraw him and make him better since he's so old and falling apart. Put him underneath.
Is a beta?
Yeah, it could be an E for beta right here, or it could be a B. Their fancy B, it's a...
Positron? Wait, what's the definition for a positron?
So positron is a positive electron. And a neutron is just a neutron.
The proton, is it next to it? Is it a 1 on a 1?
1, 1.
Okay.
1, 1 hydrogen. Okay, has everybody got all these down yet? Almost? So we're going to come back to this page. So you might want to square this or make sure you know where this is, because this is going to be important that you know how to do this for the equations that we're going to do with nuclear. So we have been doing chemical equations that are working with their electrons, but now we're going to be working inside the nucleus and working with protons and neutrons and figuring out how they change when an unstable atom falls apart. Okay, we ready to go forward? Okay, so just to review, you've been having questions along the way of how to set up an isotope and what do you put on the top, what do you put on the bottom. We learned the very first of the year, and I've just been throwing in review questions as we go. Remember, the top number is your mass number. That's the number of protons plus neutrons. The bottom number is your atomic number. That tells you what element is on the periodic table and how many protons. And then your element is a symbol. There are 3 elements that are isotopes that have their own name. It's protium, protium, deuterium, and tritium. These are the only isotopes that have their own names. Other isotopes we would just write like this. Now, if they give you the symbol, they don't have to give you the atomic number because you can find it on the periodic table. Okay? Going forward, we're going to write some isotopes just so that we remember how to do that. So if I have iodine 131, how would I write it as an isotopic symbol?
What was the symbol?
Isotopic symbol.
Yeah, what was that?
The nuclear isotopic.
So we would write the symbol for iodine, which is I, and then on the top, what do we write? The mass number, and what do we write on the bottom? The atomic number. So what number is iodine on the periodic table? 53, and I'm done. That's the isotopic number. That's the isotopic symbol. So what was the beta particle? See if you can do it without looking back. What do we write for a beta particle?
It was like 1, 0, with a B or something.
So I had a B, had a Z, -1, right. Okay, so what would I write for the isotopic symbol for uranium?
For uranium, it would be U to on the top left.
Got it. They're usually on the very bottom, so you're looking across the bottom. Or they're in the lower P area for the most part. Okay, so we know how to write these. Now we're going to start doing equations. Equations are really easy. Treat the arrow as an equal sign. The top on this side has to equal the top on this side. The bottom on this side has to equal the bottom on this side. So on the top we've got 196 plus 0 equals 196. On the bottom we've got 82 plus a -1 equals 81. What element is 81 on the periodic table? Thallium. Done. Okay, see if you can do B, C, and D. I'll give you a minute for each. So you add the top, the arrow acts like an equal sign. Add the bottom, the arrow acts as an equal sign. It has to be the same on both sides.
Why are you writing it like this? It's really easy for now. It's TL.
It's TL.
Oh,
It's TL.
that's what it is. Okay.
Okay, so this one is.
So we got 28 is equal to 0 plus
This is sulfur.
28.
Oh, wait.
And then we got 15 is equal to 1 plus 14, which is...
Why is it 1
plus 14? 15?
It's 15.
So 15 is equal to 1 plus 14, right? 1 plus 14 is 15.
Silicon.
It's nickel.
Nope.
How is it not nickel?
Okay, so look. 28 is equal to 0 plus 28 on the top. Bottom. 15 is equal to 1 plus
It's silicon.
14. So 14 is silicon. Okay, so try the next one.
This is Powell.
Yes? Yes?
And J.D. Rooks to the attendant's office. He's being checked out.
Okay. All right, so JD, you want to watch this online? Let me give you a cup because you're going to have to do this at home. Skittles or M&Ms? Okay, so I'm giving you 2 cups and a paper towel. You're going to need to do the M&M lab at home. Okay, so read what it tells you to do and then do that. Okay, you got it? Let's see. I want a thumbs up if you got it right. Thumbs down if you didn't.
Boom, let's go.
Thumbs up. I want to see. I only see a few thumbs up. I want to see everybody's thumb, either up or down. Yes, I got it. No, I didn't. Okay, we're going to try again. Again, 73 is equal to something plus 30 is equal to -1 plus. Okay, get it figured out. Try and do it on your own. Do not put a divide sign between the numbers. Nope, think -1. You got to add 1.
Like adding some like something to add to this to make it better.
Because 31 minus 1 is 30. This is your equal sign. Okay, got it? How many got it? Thumbs up. I want to see everybody's thumb. I want to know if you got it or not. Okay, if you are thumbs down, do you understand what you did wrong? Okay, where did you go? Okay, so 73 is equal to 0 plus 73. 30 is equal to -1 plus 31. So bottom number tells you what element it is all the time. Okay, let's go forward. Another kind of terminology. So when we work with radioactive elements, we always start with what is called a parent. A parent is one that's unstable. It's going to radioactively decay. When it decays, it becomes a daughter. It doesn't become sons. Sorry, no sons. So it becomes a parent, then a daughter. If a daughter is still unstable, it can produce another daughter, which can produce another daughter, which can produce another daughter. So there's always just one parent and then daughters. Okay? You're always going to get some kind of particle coming off. When I work with a positron is an anti-electron. How many are Star Trek fans? Anybody? Okay, so you know about Data, right? Data's brain is positronic, which means instead of it working on electrons, it works on positrons, which are antimatter electrons. Okay? It's a counterpart of the electron. It has a +1, E, and it has a half spin of a half. And it has the same mass as an electron. Excuse me. All right, going forward.
Oh, frick, we're supposed to write that.
Yes, you were supposed to write that down. Usually when the things are different colors, that means you have something you need to write down. Got it? Okay, going forward. Okay, electron capture. Whenever you see capture or bombard, those words tell me to put it on the reactant side. If you see the words decay, emit, produce, these are going to be on the product side. So we're going to need to know that terminology so when we go to make an equation, we know what side to put the particles on. Okay, so an electron capture is a mode of decay from some unstable nuclei in which an electron forms outside the nucleus, from outside the nucleus, it should be, not form, from outside the nucleus when it combines with a proton to form a neutron. So the electron is shot at a particle. As it hits that particle, it combines with a proton and flips that proton into a neutron. Okay, so we need to know those words. Okay? All right, going forward. Now, the thing you need to know about electron capture is it just doesn't give the particle that you think it would. It also gives a gamma. So you're always going to have a gamma whenever you have an electron capture. So would you see if you could figure out what particles, one of them being a gamma, are on the other side? Stay awake, stay awake. Okay, write it down. Let's see if you can figure it out with everybody. Everybody get a chance. Okay, got it?
Yeah.
Got it? Thumbs up. I want to know. Are you getting it or are you not? Thumbs up, thumbs down.
Second one.
So I told you it wasn't a gamma.
I know, but
So I told you anytime you have an electron capture, you're going to have a gamma plus
Yeah.
something else.
So the gamma is like, how would you figure out the gamma?
Gamma's a 0, 0. You just need to know that it's there. It's always there for an electron capture.
a gamma period, like that's just gamma.
That's what gamma is. It's just, you just write it like this, and it's a 0, 0.
Oh, it's
Done.
a fish. Oh,
Yeah, it's basically a fish swimming down.
that confused me. So I was like, how was it?
Okay, do the second one. Let's see what we do with the second one. I want 100% thumbs up.
Oh man, what's
Is it always gonna be like that? The gamma?
Yep. Sometimes they do not write the 0, 0 on the gamma. Sometimes they just write it like that. Okay, we ready?
BK.
Anybody need some more time? Coming in 3, 2, and 1.
Oh, let's go.
Thumbs up, you got it. Thumbs down, you did. And I want to see everybody's thumb.
Oh. Wait,
You're not trying.
wait.
I
95.
believe
You got to stay with me.
Wait.
Come on, you can do this.
95 minus 1 is 94.
96 minus 1 is 95. The arrow is the equal.
Okay.
Okay, yes.
Never mind. I don't never remember trying to recite.
But I thought it was like, oh,
'Kay.
that and that. Never mind.
Okay, let's go ahead. All right, so now we're going to write it without having the whole equation or even part of it. We're just going to start with something and say what it does. So, iodine 122 will undergo a positron emission. Okay, what's a positron? First thing.
Positive
That's
electron.
like you.
Positive electron. So it's going to be this, right? Or you could write it 0 plus 1 beta. Emission, what side is it going to be on?
Wait.
Product side.
Product side.
Okay, now write me an equation.
So wait,
Finish it.
it's adding 0 plus 1.
So start with your iodine, then put your arrow, then put your positron at plus what?
Wait. Ah. Okay, one.
So then it's 0 plus 1. And then,
Okay, I'm confused.
so then you still do
So start with the iodine, then put the arrow, then put a beta, whichever one you want to use, the positron,
and then it's plus.
and then plus something.
So you find the element.
Plus whatever you need to make it so it adds up to what they're equal on both
How can you
sides.
put it on the product side?
You're going to put it on the product side. So arrow after the iodine, and then put it on the product side. You're going to have two things on the product side.
Boom, got it.
And then what do you, oh.
Whatever you need to make that balance out, because that's not equal to the 122 over.
So could you finish the equation then?
Yeah, you finish the equation.
Okay.
Finish the equation.
Problem?
Yeah, if you get done with the first one, go ahead and on to the second. I'm going to have you stop every minute, and I'm going to put it up, and we'll see how you're doing.
So beta particle is negative, right?
0, negative 1, B. Okay, so first one, here we go. Let's see how we did. I want thumbs up or thumbs down from everyone. Here we go.
Okay.
Thumbs up or thumbs down? From everyone.
Let's get it.
Oh.
I got it. Like
Okay.
last second.
All right, we're working on the next one. Beta emission. What's a beta?
Isn't it like 0 minus 1?
So it's a minus 1 instead of a positive 1. Doesn't want to go off there. Okay, so one of those two. Yes, ma'am.
How do you know if it's going to subtract? Like, I know that it's like a positive, but why would it subtract?
It doesn't subtract.
Or like, because
53 is equal to 1 plus 52. Remember, the arrow is the equal sign.
how do you know like what is or isn't like?
So that's why I gave it to you on that page and told you to put a square around it. That's what you got to go back and look and see what it is.
Beta emission, it would be like something plus negative 1, so technically you're minusing something, you get 6. So then that'd be 9.
It would be what?
Would it be 7 or would it be 7?
It would be nitrogen, yeah.
Well, how come up here
So
for this word, it was, oh, is it because it's on
the reactant side. Mhm.
Okay.
Okay, let's see how we did on number 2. You ready? Nope, not ready. Okay, take a minute. I want you to have a chance. If you're already done with number 2, go on to number 3.
Okay, I got it.
We're going to check them, though. I want you to check them. 30 seconds. We're going to check this one. Yes.
For electron
One of these two, but it's on the product side.
What's the equation for an electron?
Oh, for an electron, it's either one of these.
Electron capture?
Yep, but it's on the reactant side. Okay, here we go. Ready?
Wait, is it the negative or the
The
positive?
second one is what we're doing.
Wait, is the third one the positive or negative?
Negative. Okay, here we go. Let's see. I want to see a thumbs up or thumbs down.
Oh, yay.
Thumbs up or thumbs down. Everyone. Connor. Thumb up or thumb down. Oh. Okay, let me know what you need.
If I put it for E, will that be wrong?
Yeah, if you put it either, that's fine.
So for electron capture, going to be an element that's in the
Electron capture is just putting this on the reactant side.
So that's first.
Wait, that goes on the. Oh!
So electron capture, I'm capturing this electron, I'm putting it on the reactant side. Okay?
Beta thing goes on.
This goes on the reactant side
So then it's plus 0, negative
because I'm capturing it. Or if I bombard it, then it goes on the reactant side. Yes.
Then would it be like beta plus 55, whatever?
Right, yields, whatever.
So it would be Virial minus E. And
Would
then
it be 25?
yeah.
I'll show you in just a minute. So what are we having? Are you understanding this? Or? Five, 4, 3, I'm giving her some time, 2, 1, boom.
Yes! Let's go.
Thumbs up, I got it. Thumbs down, I didn't. Do you know why you didn't get it right?
Wait,
Yes.
wouldn't it be plus the gamma?
Oh, yes, thank you. It would be plus gamma.
Wait,
Good
so
job.
it would be magnet, whatever that one is.
Mac
It'd be plus the
Manganese,
plus 0, 0,
Yeah,
y.
wait, I'm so confused.
Wait, why is it plus gamma? Because it's.
because it's an electron capture. You guys are the first ones that caught that all day long. That's awesome. Good job.
Oh, I was gonna have it.
Okay, so what do we got? We okay? Do you understand what you did wrong if I saw some thumbs down this time?
Just call her bro.
So 55 plus 0 equals 55. 26 minus 1 is 25. 25 is manganese.
It sucks because I write my zeros.
Okay, now we're doing the next one. Alpha. What's an alpha?
Alpha.
4-2 helium, or you can write 4-2 fish. Yep.
4-2 fishy.
Remember not to put divide lines in between them. Yes.
So for this one, would the alpha be first then? Would it be on the reactant side? Alpha doesn't
Yeah.
Emission, it's going to go product. Emission, it's going to go product.
So wait.
Yes.
Instead of HE, could you put
The fish?
the sign?
Yep. This is this or this. This is the alpha sign. Yeah, that's the fish sign.
Oh,
So would it be that, would it be then it yields
Mm-hmm.
alpha plus,
Would it be mercury?
Well, let's see. Keep going. Okay, I'll give you another 30 seconds. Go.
I'm so good.
wait, why would it be,
I'm so
wait, for the,
Yes. So put 4-2 in there.
yeah, so wait, for this one, would you use minus 2 then? So we go back to mercury?
What?
yes.
I got it.
So over here you got to have something plus 2 equals that. Something plus 4 equals this.
Wait, so something plus,
Something plus 2 equals this. Something plus 4 equals this.
okay.
Okay, we got 12 more seconds and we'll show.
Oh yeah, let's go. 4-4, let's go. I'm ready.
You're so dramatic.
Let's get
You
this
see,
started.
something plus 2 equals 84?
Yes.
I think this is the first time.
I've never seen anyone so hyped about chemistry.
Okay, here we go.
Not even in this house.
Let's go!
Okay, that's what I
No, this should be 82. Sorry, I didn't fix that.
That's what I thought.
Should be 82. Should be 82 on the bottom.
Why is it?
I know.
Oh, wait, I did that wrong.
4 in a row.
This bottom number should be 82. Okay, we ready? Turn the page. Da-da-da-dum. There's 4 more. You do them. I'll put them up every minute. Yep, it's on by my little calendar on my computer thing. By the lotions. Can you reach it? Oh, they were there.
Oh, there.
Oh, they are. Yeah.
Thank you.
They got bumped down.
So then, would it be right for this one then? Or this would it be this? Going to Chrome. Oh, yeah. Okay.
Hey, who's got the first one done? Anybody need more time with the first one? So put a plus instead of an equal. So put a plus instead of an equal. Okay, here you go. Let's see. Thumbs up.
Wait, whoa.
Just the first one.
I know. Wait. Okay.
Okay, here we go. Thumbs up if you got it right. Thumbs up. Thumbs down if you didn't. All right, let's keep going. Work on the next one. I'll give you a minute. Are you getting this?
Oh,
Okay, so let's do this. So put that right here. And you can then go plus because it's a capture. And we're going to go 0, -1e, or 0, -1b. Doesn't matter which we use.
Okay.
Oh. So like this. 0, -1b. Like that. And then that's going to equal 54 plus 0 is 54 on top.
Okay, let's go.
And 25 minus 1 is?
24.
And then you look on the periodic table and find number 24.
Deal.
Okay, let's see what we did. Ready? Set.
Boom!
Wait, would it be?
go.
Would it have the gamma thing again?
Yeah, plus
Yeah.
0, y.
You got me again, plus gamma, yes.
Heck yeah!
I'm actually getting you ready to just
The other way around.
Capture. This one, electron, is captured, it's on the reactant side. Captured or bombard is on the reactant side. Emit on the product side.
Yeah, so should it be on this side?
Capture, it's on this side. Okay, look at the next one. Beta emission. Now we're going to emit a beta.
It's on the reactant.
It's on the product side, so put a beta on the product side. So start with what you were given,
Oh yeah, that's the product.
then put an arrow, then put your beta, and then whatever else you need to balance it.
what to do.
Oh, wait.
To go to this, would it go to 220 and then this will go to 86? Or would it go?
Mm-hmm. Yep.
Can you help me?
Mm-hmm.
I'm not getting, like, I know this goes, but, like,
Go put that first.
this,
Yep.
but it's not the same thing as the other.
So beta, it's going to be an emission, so we're going to do an arrow right away. And then put the beta on there. So 0, -1e or 0, -1b. Plus, what else? So 56 equal Nope, because you're going to subtract 1.
Yeah, 24. That's a
25 is equal to negative 1 plus 24. That'll be 23.
Yeah, so 26.
Okay, let's see what we can do. Let's see how many we got this right. This next one. Here we go. Thumbs up or thumbs down? Oh, I like the thumbs up. It's awesome. Okay, we're doing the last one.
How'd you get 26?
So 26 minus 1 is 25.
Okay, sweet.
Remember that this is my equal sign, right?
But 20. Oh, that's
26 minus 1 is 25.
And then on the top it says 20. Okay.
56 equals 0 plus 56.
This like gets me every 2 problems. Like,
Okay, go ahead and go to the next one. It's another emission, so put an alpha on the product side. Emit on the product side. Okay, keep going. Let me help you. I'll go sit down on the other side. Okay, so your emission, so arrow. Anytime you have an arrow, it's just going to be write down what you have, put an arrow. A beta, which is this.
Whoa.
And plus something else. So that something else is going to be 56 is equal to 0 plus 25 is equal to negative 1 plus 26. Because 26 minus 1 is 25. So you got to think backwards a little bit. So that's still 20. It's 26 though. Whoa. Throwing pencils. And then 26 up there is FE. Okay, now we're working on this one. So we started here again with this. And it's an emission, so we're going to do right the arrow. And the alpha is 4, 2. So 4 on top, 2 on the bottom. And HE, helium, plus what else? 220.
oh, wait, you subtracted?
Yeah, well, 224 is equal to 4 plus what? 220.
Okay.
88 is equal to 2 plus, nope, the other way. Yep. And then look up 86 up there. Okay, we ready to check the last one? Here we go. Ready? Want thumbs up or thumbs down from everyone?
Yeah.
Thumbs up? Do I have any thumbs down?
No, I've gotten an E out of.
Oh, got a couple. Okay, so if you're having problems with this, we need to probably sit down and go over it. We're going to go now into half-lives. Radioactive isotopes have half-lives. We're going to use easy stuff here. Basically, we're just wanting to know how much time it takes for half-life. Okay, so we're going to use a couple equations. Before I want to get it visually in your mind, we're going to be doing a lab with this. So if I start with 4,000 of something, I wait until it's 2,000 of something, and however long that took was a half-life. Then I take that 2,000 and another half-life, I would cut in half and make it to 1,000. It's the same distance. So you see that's 10 minutes for every half-life. As I get down here, I'm never going to reach 0. I'm always going to have some little bit left. Okay? All right. You'll notice up here that half-lives can go anywhere from, there's actually ones that only have milliseconds to ones that are billions of years. I just put a couple for example up there. So these are the equations we're going to use. I have rearranged them. So you'll need to add this one to your chart. You'll need to add this one and this one to your chart and the explanation of them. So go ahead and add them so that you have them. I like this little mathematics. Yeah, it's on there, but I've rearranged it so you need to add it in. So you don't have to rearrange them on your own. Okay? I like this little mathematics of life. Life plus love equals happy. Life minus love is sad. 2 lives equals happy plus sad. Therefore, happy plus sad divides by 2. Therefore, half happy, half sad is what life equals. That's real life. Enjoy it.
So you want us to put that under like the mathematics of life theme?
Yep. So I've just rearranged them to make it easier for you so you don't have to rearrange them on your own. Because I know that some kids get messed up when they try and rearrange even with 3.
Wait, does the capital and lowercase matter?
Yeah, capital T is total time, lowercase t is t1/2, or the half-life.
What's that schedule on the the sophomore testing.
Yep.
It starts on Wednesday.
It's on Wednesday, Thursday, Friday, Monday. Tuesday's normal schedule. Wednesday, Thursday, Friday, Saturday, Monday. Yeah, it's really weird. No. No. No, it just means some classes are going to be like 5 or 10 minutes longer, and other classes are going to be 5 or 10 minutes shorter. And it spirals, so like if fifth period gets shorted 5 or 10 minutes, then the next time it's 5 or 10 minutes longer. It's just really weird. Schedule gets really whacked.
Because they finally decided they want to do something where they haven't done this before. So
It's because they're testing sophomores for English, reading, math, and science.
they've never done this before.
No, this is a new one. It's replacing the SAGE testing.
Everyone just goes to class like normal. It's just some, like the sophomores.
Okay, so we're going to go forward. Everybody got these down? Hurry quickly. Make sure you've got all this down because we're going to use it. They can't because some of the tests are longer, so they've got to have some periods be longer so they don't interrupt a test.
And the tests don't stop. It's just like the sophomores are testing all day. I know those poor will be brain dead when they're done.
Yep. Okay, we ready? Okay, so we're going to do some experiments with this. So you can sort of see if I start with 10 grams, then I go to 5 grams, and half of 5 grams is 2 grams, half of 2.5 grams is 1.25 grams. So I just keep going with the number of half-lives. This is carbon-14. When they say they've radioactively dated something, they usually use carbon-14. But they only usually use it up to 4 or 5 half-lives for carbon-14. If it's older than that, then they've got to use something else. Because this goes exponential and never quite reaches 0. But as the exponential curve gets flatter and flatter, the percent error goes up exponentially. Okay? So, here we're going to do an experiment, or an example. Rubidium-79 decays by positron emission and forms krypton-79. And we could write that out as an equation, but we're not going to do that right now. We're working on this other stuff. So, we weighed 100 milligrams. That's AO. That's AO, the beginning amount. A sample of solid rubidium was allowed to decay for 42 minutes. This is our total time. I'm sure you can. You may. Its mass was 25 milligrams at the end. That's A. And we're looking for the half-life, which is T1 half. A0 above the 100, yes. So I'm going to use the equation really quickly. A0 divided by A equals 2n. 2 to the n power, sorry. So if I plug in, I've got 100 divided by 25. Everybody should know the answer to this. 4. There's 4 quarters in a dollar, right? Okay, so 2 to what power is 4? 2 times 2 is 4, right? So n here is 2. That's how many half-lives I've undergone in 42 minutes. So to find the T1 half, I'm going to use the equation that says time total divided by n will give me T1 half. So I've got 42, whoops, that's a lovely 42. 42 divided by 2 will give me the half-life, which is 21 minutes. Okay? How did that equal 2n? This is one of the things I had you write down.
So you could just like take the 42 and just divide it by 2 and to give you the half-life, but you gotta like write the whole thing down.
Well, you've got to know how many half-lives you've undergone.
And how do you know like
So you could divide it by any number, but that doesn't mean it's what you want. Okay.
what they are, like the A0, the A?
So A is 0 is what you start with. That's the definitions that we wrote down just before this.
Oh, okay, sorry.
It's okay. All right, so let's do the next one. Positron decays by positron emission, or potassium-38 decays by positron emission to argon-38, a gas. If we have a half-life of 7.7 minutes. So this is T1 half. How long, so we're looking for T, will it take for 200 milligrams, that's A0, or the amount initial, to reduce to, here's my A, 25. So we're going to use that same setup we did before. AO over A, which is equal to 2N, which is equal to 200 divided by 25, which will be what? Okay, 2 times what power is 8? Well, 2 times 2 is 4 times 2 is 8. So N is 3, right? Okay, now what do? I'm trying to find T this time, the capital T.
You do N times.
I want to find T total.
You do N times T half.
Good, so T1 half times N, and that would be 7.7 times 3. What am I going to end up with?
It's like, isn't it like 21?
23.1, good.
But 7.7 times 3?
Is it what?
7.7 times 3?
Yep, 7.7 times 3.
Why is it? Oh, just kidding.
Everybody understand how I did that? Okay, let's go on to the next one. Okay, suppose a sample gave an initial reading of 120 units. Now, they can give you this because, how many have watched Ghostbusters? You know that thing that they hold and they have that thing holding out? That's just a Geiger counter. That's just telling me how many hits I'm getting per second, how many things are decaying per second. Okay, so they're saying 120 units is the activity. I'm getting 120 units constantly. It took 35 minutes, so this is AO. It took this much. That's my total time. For the reading to drop to 60 units. What would be the half-life, T1 half? Well, what does T1 half mean? How long does it take to cut it in half, right? What just happened here? It cut in half. So I do need to do any math? No. I can just say, oh, T1 half is what? 35 minutes. Because I went from 20 to 60, and that's half of 120, right?
Oh. So why would it be 30?
Because that's how long it took for it to get that way.
Why not?
T1 half is always a time. So I went from 120 to 60, and that's half of what I started with, right? Okay, let's look at the next one. We got to use a little brain power here, just a little bit. Okay, the activity of a radioactive substance is measured at 9 a.m. At 5 p.m., what's my distance in time?
8 hours.
Yeah, 8.
8 hours.
So T total is 8 hours. So that's my little brain power. Okay, I should put an S on that. The activity is found to be only 1/16, so that's after time of the original value. So what would A be? 1.
How?
If only 1/16 is left, how much do I start with? A whole. Okay, so I can do this one of two ways. I can set it up like we did before, AO divided by A equals 2 to the N, which would be 1 divided by 1 divided by 16, which would be equal to 16. Okay, so I got, how many times 2 do I get to get to 16? Well, 2 times 2 is 4, times 2 is 8, times 2 is 16. So N would equal 4. I can also look at it and say, okay, I started with 1. If I cut it in half, it's 1/2. If I cut that in half, I get 1/4. If I cut that in half, I get 1/8. If I cut that in half, I get 1/16. How many times did I cut it in half? 1, 2, 3, 4. So there's two ways you can look at it. Okay, so I have 4 half-lives. I have 8 total hours. So T1 half is equal to T divided by N. So it's 8 divided by 4, which is 2 hours. That's my half-life. Okay, where did I lose you? So down here, I just did it 2 different ways. I could do it the way on the top, where we've done it before. A0 divided by A. And I could find out t to some power equals 16. And go 2 times 2 is 4, times 2 is 8, times 2 is 16. I get 4. Or I could say, you know what, I started with a whole. So I started with a whole. I went to a half. I then went to a fourth. Then I went to an eighth. And then I went to a 16th. How many times did it take? 1, 2, 3, 4. So it depends on if you're visual or if you're mathematics. I am not an artist. Okay, we figured there was 8 hours. Then we just take the 8 divided by our number of times we cut it in half, which was 4, and we got 2 hours for a half-life.
So, do you think it'd be easier, like, or more simplified to, like, the top way instead of the bottom way?
It's up to you. If you're mathematically, it's easier the top way. If you're visual, you got to think of the pie. Okay, I cut it in half. Now I cut it in half again. Now I cut it in half again. I cut it in half again. It's up to you. Because they did a fraction, they said I had 1/16 left, and I must have started with a whole. Right? I must have started with one whole.
That makes more sense.
So I started with one big pizza.
So you don't put 16 for one?
Right, for the original. 1/16 would be my ending amount. Okay, so let's go ahead and go forward. Let's talk about radiation just for a second. Radiation, if you are irradiated, there's some things that can happen. As long as you stay down below 20 millisieverts, you're fine. There's nothing really that's going to happen. Okay? But once you get above that, things can start to happen. Your level of cancer increases. Lots of things can happen here. If you get above 2,000, then you've got acute radiation sickness, and half people are killed within a month. You know, things can be fatal within days. So when they take people into cancer radiation treatment, they're actually taking them to the edge of death and hoping that they're not one of the 50. And then to bring them back. Because they're trying to kill those fast-growing cells. And hoping that there's enough good cells left over to bring them back. So when they have bone marrow cancer, they kill the bone marrow, and then they have to have a bone marrow donor give them bone marrow back so that they can redo. Yep. There's lots of different radiations. For different cancers, they use different radiation sources. Okay, so let's go forward here just a little bit. Remember our picture what said, you know, how much radiation will get it through? When you go to the dentist, they put this apron on you. It's full of 0.5 centimeters lead. And that lead is usually encased in zinc because they don't want to give you lead poisoning, but they want to stop the radiation. So that's what's going on there. If you had 10 of those aprons, you know how heavy they feel when they put them on you? Think of 10 of them on top of you. Okay? That's what they need to stop gamma rays. It's really hard. You wouldn't be able to breathe. Because even with one, it's sort of hard to breathe. You think of 10 of those, it'd be too much. Okay, so going forward, what happens when we get hit by radiation? When we get hit by radiation, our DNA is damaged. Now, many of you will have DNA damage in the next few days, especially when it's sunny. What am I talking about? Sunburns. Okay? So you're damaging your DNA when you get a sunburn. So, and
What does it mean by damaging your DNA? Like, what does that do?
so there's some things that can happen. You have damage when you get a sunburn. Your body has two choices. Okay, actually it's three. It can actually cause cell death. If you have too much radiation, it causes cell death. Okay, and you get blisters and you get all kinds of sores. It can repair. You can get a sunburn and repair. Fine. Or it can misrepair. If it misrepairs, that's where cancer comes. So that's where melanoma, carcinomas of the skin come. Okay? Now, we used to think that, you just spread Crisco on your skin, go out and get a good tan. That's what we used to do. So, but yeah, Crisco. Well, we wanted the brown. We wanted to tan, That was the thought back then. But now I've got 3 sisters that have had melanoma cancer taken off. I've had part of my ear taken off with basal cell cancer because of it. it's a long-term thing. It doesn't happen right away. You might think it might be cool to be tan, but I'm telling you it's not cool, because we sort of laugh because the dermatologists are not, what's the word? Plastic surgeons. And when they go take out a cancer, they just give a shark bite, is what we call them. There's shark bites, and that's what that looks like. And if you want it to be nice, you have to go to a plastic surgeon and have them fix it. Yes.
So you said like just anything can like damage it. So like if you just like naturally tan, then it's still like.
It still can. You can still get it. Yeah.
Oh, is that what sun lotion is like?
So sunscreen blocks those UV rays.
But I know these things.
Yes.
So you see like if you tan like different parts, like for example, when we went to Disneyland, I got tan line in like 30 minutes because I hadn't seen the sun in like months.
Hmm.
That's like.
That's damage, skin damage.
What about tanning beds?
They are the worst that you can get.
Yeah.
It's straight UV rays.
It's straight UV rays, and so you're just opening yourself to cancer all over your body. Yep. So if it has sunscreen in it, that number next to the sunscreen, that tells you how long you can be out in the sun without re-putting on the sunscreen. So if you have SP 10, that's 10 minutes.
Oh wait, so SPF 15.
15 minutes.
What?
It protects you for 15 minutes, that's it.
Like usually it says like on the back like how often you should reapply it. Yeah,
Hmm. Yeah.
because everyone says like
Yep.
SPF
Yep.
50.
So you've got to reapply and reapply and reapply.
People think you're good, like they
Yep.
do it on you one time and then like.
Okay, so let's put the rest of this down and get going on the, we're running out of time. So radioactivity can't be detected by senses. We can't see it. We don't know it's there, but it is damaging our cells. Okay? Nuclear radiation will damage or kill rapidly dividing cells. Rapidly dividing cells are bone marrow, skin, and reproductive and intestinal. Those are rapidly dividing, and that's what the radioactive isotopes hit first. Cancer cells divide rapidly. Because they divide rapidly, radiation is a good source to kill them. Food is irradiated to exposed to gamma radiation to kill any organisms on there. If I want to get strawberries from California to New York, the only way I'm going to do that and still have them nice is to irradiate them. Yes?
So yeah, like if you nuclear radiation, because like nuclear radiation is like, that's for like cancer. Like, actually, I haven't get personal or anything. My grandma had like cancer and stuff, and like they would have to get like in the brain, it'd have to be like radiation, because like that's like all they could do.
Mm-hmm.
So from like spreading.
Did they use the seed crystals or not?
I honestly don't know what they use.
They usually take and put a seed crystal in a needle
Yeah.
and inject it where they want it.
I think that's probably what it was. But like, would that like damage the good parts of the brain?
It can.
Yeah, that's what I said. Cause like she had like
Memory loss.
she had some memory loss.
Yep.
She gets third remember that.
Okay, one thing I want to clear up right now is people think that when food is irradiated, it's radioactive and you can't eat it. It only kills rapidly growing cells. Once something has been picked, is it growing anymore? No. So it won't kill what it has been picked. It will kill the E. coli that might be on it. It will kill the bacteria that might be on it. Yes?
So why does it kill only like rapidly dividing cells and not?
That's just what it does.
Is there any
I don't know the why.
you could find anything that would kill like the slowly dividing cells? Because if it only kills rapidly killing ones, then they'll still.
Wait, what do we put for this? What are radiation?
Slowly dividing ones will still have like a chance to do things.
Right. I don't know. There's tons of new things going on. If you've ever been down to the Huntsman Center, they've got all kinds of new stuff going. Okay? Yes?
What do we put for what are radiation's effects on health?
So radiation's effects on health can be your eyes, your ears. That's sort of what's about that. We got to hustle, guys. Okay, so the average radiation that a person gets per year is 0.27 rem. 0.27 rem. Generally, at that point, there's no biological effects. A rem is a way to measure it, how it affects the biological. There's several different ways that they measure radiation. REM is one of them, Sievert's one, RADs are some. It just depends on how much radiation there is on
So
how it
it's
affects.
It's like 0.27 rem. Is that like?
That's very small.
Oh, that's
Very
very.
small. So at that point, there's no, up until 25 rems, there's really no detectable amount. A single dose of 25 to 100 rems causes a slight decrease in white blood cell count. So if your doctor orders a CT scan or PET scan, that will happen. Or CAT scan. Okay. A dose of more than 100 rem causes radiation sickness. So they got to be careful. They can't give you MRI after MRI after MRI, or a CAT scan after CAT scan after CAT scan. When you see LD, LD means lethal dose. Okay, LD means lethal dose. If you see a pesticide at home, if your mom or dad sprays like Roundup or that, it'll have an LD on it. The number next to it says that if you are exposed to this, that's how many out of 100 would die.
What do you mean? 50 people?
If it's like LD 50, like
50%. Right.
Wait, what do you mean?
So-
half of what?
so what can you not do?
So
You can't be around it.
it's if you get enough of a dose on it, 50% would die.
Wait,
You just like
50%
accidentally
of
spray
what?
it on your
People
body.
or like?
No, as long as you rinse off and stuff. But there's a thing that's like LD 54, and then it will tell you how much. Okay, so when they say, use pants and shoes, don't spray in shorts and flip-flops, there's a reason. Okay, so you don't get the overspray on you. Okay, all right, so having said that, we're going to head into our nuclear decay lab. We're going to have to be fast. So, we're doing M&Ms or Skittles. Now, each of you are going to get a cup of M&Ms or Skittles. Okay, you're going to take that cup, you're going to dump it on to a paper towel like this. You're going to sort of push it so they're all on one level. You're going to count how many you have. After you count how many you have, you're going to then take the ones that are S up and put them into, you're going to have 2 cups by the way, into a cup. This cup that has the S or up in it, put it aside. Remember that number, it goes on your paper. Would you flip your paper over really quick? There is a table. And at the table at the top it says trial 1, trial 2, trial 3. So if I do trial 1, I would count all my Skittles. And I'd write that number on the top for 0 on all the way across. Okay, then I go back to trial 1. I count just the up Skittles and I put them into 1. Okay? And I put it on number 1, the one that had the S up. So you can either see the S or you can't see the S. If it's S down, it's not radioactive anymore, you put it in another cup. Then you take the ones that were radioactive, shake them, dump them out again, count the S up again. Put the non-S up down.
Would that be like trial 2? Like
That would be trial 2. So every time you count, you're going to put down until you get to 0. You have none that are S or M up. Then you go to the second trial and do it again. And then you go to the third trial and do it again until it goes to 0. Okay?
Until what goes to 0?
Yes.
So we're gonna like shake it into like.
So in a column, you shake it until you get down to 0 S up or M up.
Can we tell like how many times we shook it, or?
No, each time you shake it, you're going to count how many you have and put it on that line. So the first time you just count how many total and put it on the 0 line. Then you're going to dump it out, pick up how many S's are up, count them. That will be on row 1. Then you'll take those, shake them again, dump them out, count how many are S up, put them back in. The rest put in the thing like this. No, you might not get down to 20. You might stop, you might be zeroed out at 4. Or you might have 1 for 5 in a row before you get to 0. Okay, but you're going to do it 3 times. We have 10 minutes. Come get it and pick what you'd like to do.
I don't know.
You're all doing your own.
Oh, these are cute. I got the own M&Ms.
Yeah, M&Ms went faster than I thought they would. They're more expensive, so I didn't get as many of them. Paper towels are already cut for you right here.
And then we need another cup.
And you need a blank cup. So you need a cup of Skittles or M&Ms and a blank cup. Get going as fast as you can. We'll finish this lab up next time. You'll have some time next time to work on it. But you got to get this first part down. Got to get your 3 trials down.